Okay, let's come to order. We can, I think we can agree. Can we agree on that first one? 4/3. Yeah, all right. Okay. Everyone okay with that? Make sure it's centered at 2. All right, now the second one. The second one presents for us a little bit of an interesting discussion. Let's see. It says, use the third order Taylor approximation polynomial to approximate that. So that's good. Is that what you guys got? I think I got that too. Actually have a 0.198. Okay, good. That's right. Now here's the question: what is the error bound using this? Well, we can use so you use 3 plus 1, so using the fourth derivative, everything, and right? But actually, we can actually say something even more strongly on this one. So this is fine. I think this is okay. What Victor did, and I think that's probably what everyone did. But we can actually say a little more about the error on this one in particular because of another interesting fact about this particular series. This is not just the third order polynomial. This is also the fourth order, isn't it? Yes? So actually, when we use this to approximate, we can actually say something a little bit stronger. We can do all of this with the fifth derivative, right? So the error is actually less than this, is the point. When you use this to approximate, you actually get a little bit of we can actually make a stronger claim about these approximations than what we said here. So I wouldn't have expected you to come up with that necessarily, but now I would, right now that I've said it, just now, okay? So does that make sense? So find the maximum of the fifth, that's the value of the fifth derivative on that interval. And actually, let's see, what is the fifth? That actually that makes life easier for you too, because what is the maximum, what is the fifth derivative? The fifth derivative is actually cosine, and on the interval negative to positive 0.2, what is the maximum of cosine without a calculator? 1. All right, so actually it makes your life a little bit easier. The maximum value for the fifth derivative, which you can use instead here if you like, just because of this particular series. This is not always something you can do. But if the next term is 0, then we can make a stronger claim. Then n would be 1 for the fifth derivative, and this would be 5 factorial, and then up here, fifth power, everything else would be the same. Anyway, so if you do that, you get a slightly smaller number. I get 2.667 times 10 to the negative 6th power. Okay, so that's a little bit of a stronger claim, right? Using the same approximate, this is x minus x cubed over 6. On this interval, we can say it has a less of an error, actually. Does that make sense? What I just talked through? Okay. I like this because it kind of brings that to the forefront. We didn't talk about that nuance yesterday, but I think it's worth talking about. It's also even worth talking about the fact that if someone asks you the third order and the fourth order Taylor polynomial for sine x, that you give the same answer, right? Isn't that also interesting? Okay. Anything else you want to say about this formula? Or maybe briefly about the homework. Was there one in particular that troubled you? I don't know. You tell me. Yeah, go ahead.
If you do this, say this way on a test or quiz, would it be acceptable, or would you expect us to do it the way you did it?
Yeah, that's a good question. I don't know. How am I going to grade you? I mean, I hope you understand what we just talked about. But it is a separate question, though, how we want to treat that. I don't know. We usually aren't out to try to trick you necessarily, so I think we'd probably be okay. I don't know. To talk to my other cohorts. But, yeah, I think we'd probably be okay with this. I don't know. That would be my feeling. I'd probably be gracious. Yeah, Natalia? Is that the one? Yeah, I actually wrote down. I think you were mentioning this to me yesterday. I actually wrote down in my homework. When we talked to me yesterday, I hadn't looked at my homework. But my homework, I wrote trial and error. Right? So I actually graphed y1 in y1 on my calculator, the absolute value of the natural log of 1 plus x minus the series approximation on various things until I got it to work, right? And I found finally that the 7th order polynomial got it for me. Did you trial and error and find the same thing? Yeah, you could use the formula too. That should help. That should give the same result. Didn't though. Okay. Yeah, maybe I did it in a more simplistic way. Like I said, I just kept graphing the absolute value of the natural log of 1 plus x minus the Taylor polynomial of various orders. And and on that interval, I did that until it worked. I don't know.
Okay, so that's kind of like similar to negative graphing. How would you do it?
Okay, actually, 19 I did number 19 algebraically. And actually, that one brings up this exact point. This number 19 is this problem here, basically. It says the Taylor polynomial, the 4th order Taylor polynomial, which is this, for sine x. This is number 19. This is just like B on the warm-up. And I said the 4th order, or the 3rd order, same thing, Taylor polynomial, has a error term less than or equal to 1 over 5 factorial x minus 0 to the 5th. And again, y1, right, it's the maximum of cosine on the interval negative whatever to whatever. Did it say? Does it actually say on an interval of any kind?
Yeah. 5 to -4.
From what to what?
But error has to be less than 5 times 10.
On what interval though, did it say?
Oh, no, just have to find it.
Oh yeah, find the interval. Okay, so we're going to be solving for x in that. We want the error to be 0.0005. So this is just, I mean, we're almost done, right? Multiply by 5 factorial, you'll get, absolute value, right? You get the absolute value of x is, oh sorry, this has to be less than that. 0.5696779. All right, so that's the interval. It's about like from negative to positive a half, right?
But then if you use the score, like if you
Yeah, you have to say a smaller interval, right? Would you get a smaller interval?
Yeah.
Yeah.
So that would still be correct.
I mean, this is more correct. I mean, this is a bigger interval over which we can be guaranteed, but again, I don't know how I would grade that though. I hope you agree with me though, at least. Yeah. Okay. So those are interesting questions, kind of flipping some of these questions on our head. Sometimes we'd like to know, sometimes we'd like to know what interval we can use. Sometimes we'd like to know how far the polynomial needs to be expanded in order to get a certain approximation of a certain quality. So yeah, we can come at those questions a couple different ways. One question that we want to address today, is it okay to turn our attention away from home? If anyone wants to see my key, I can hand it to you. All this is eventually going to be so we want to turn our attention today to, we've kind of been a little bit nebulous about when series converge. We've started the discussion a little bit, but we want to talk about how large of an interval do we have. I just told you earlier in this course so far that sine, cosine, e to the x, those power series, those converge eventually for all real numbers, right? So the one that you know about, that we do know everything about, is a geometric series, right? And that I even asked you, right? I can ask you anytime I want about any geometric series. Anything that has that form, right? Even if it's kind of crazy. If it has that form, then you know R has to be between negative and positive 1, right? So that we don't have, like, there's no mystery in our minds about that, okay? But what about other series is the question today. So let's define this new number r, capital R, okay? And it's kind of similar to what we might have thought about with, it's supposed to evoke a little bit of what we've already thought about, right? If x minus our center, that's the value of that, is less than r, then we're in a place where this converges. And if r is, if x minus a, the absolute value of that is greater than r, then it diverges. Okay, but so the question would be, of course, what is r? For a geometric series, finding that value is easy. That dividing line between where it converges and diverges is easy. Okay, there are three different possibilities that can happen, right? If r is some finite number, then we're done, right? Then that's called the interval of convergence, right? We're going to be a little careful because we've kind of shied away from this a little bit. We're not sure about endpoints on these things, right? We do know that inside the open interval, at least, that it converges. If r is infinity, that is, if it converges for all values less than infinity, then of course it converges everywhere, right? This would be true. I'm making the claim that this is true of e to the x and sine x and cosine x, for instance. And if capital R is 0, then these inequalities, look at what these inequalities would say, right? What this inequality says is that the absolute value of x minus a is less than 0. That's when this converges. Okay, well that doesn't happen anywhere, except for at the center, right? And diverges everywhere else. So this is like the worst, the last one here is like worst case scenario, right? Really the best case scenario is number 2. But that would we would love, right? We love it when the function, the power series representation for the function converges everywhere. That's awesome. And this number r is called the radius of convergence, and that's like the subject of today's lesson, right? Is to try to find for a given power series what its radius of convergence is. Well, that's what I'm saying. Is at the endpoints, we're not sure. Now, we said at the center, at number 3, if we're at the center, it always converges at the center, right? But up here, we made a special point, and actually, and I should have like really highlighted this or something, right? Because this is so important that we're going to spend a whole day talking about endpoints, right? Inside the interval, inside a distance of r away, it converges. Outside, it diverges. At r. Very difficult question. Sometimes it converges at both, sometimes it converges at neither, sometimes it converges at one, but not the other. So it's a very tricky question actually to get those endpoints. But we will do a whole lesson on that. I think that's section 9.5. All of section 9.5. Endpoints. Yeah, it's that important a question. Is this notation okay with you? I mean, we're trying to say something pretty basic, I think, too, right? There's some dividing line. Yeah. No. Like I said, sine and cosine and e to the x all have, we just haven't asked you a lot about this yet, right? But we have been working with a lot of series that have an infinite, that converge everywhere. Like sine, cosine, and e to the x, for instance. Yeah. So, but you're right, we've worked with number 1 a lot as well. That's like all the geometric series ones. Natural log is another one. Yeah, right. Number 3 we haven't really seen very often. And, I mean, we will show you some of those just for the sake of discussion. But like, in reality, the one series, like the ones on number 3, are not very interesting to us, right? Like, if it doesn't really converge anywhere but the center, then how useful is that series? Not really, right? Okay. So like we already said, we know everything about geometric, all right? We're talking here, and we can actually call big R, little r, our common ratio. We should also remind you that derivatives and integrals of those functions have the same radius of convergence. So we get a whole bunch of activities like that, you know, like inverse tangent has the radius of convergence of -1 to 1, the power series representation for that, because remember how we got that? We used the geometric series. So if you take the derivative of a geometric series, you get something that isn't geometric, but its radius of convergence will still be the same as the corresponding geometric series that you got it from. Same with if you take the integral. Okay, so just a reminder about that. Okay, but really what we're interested in, what about all these crazy ones we've been dealing with in the last couple days? We present to you the ratio test, which some of you might remember from pre-calculus as well. Okay. This is it's all we need. It's all we need. All right, here's how the ratio test goes. If a series is geometric, then what is this? A sub n plus 1 divided by a sub n. That's just r, right? If a series is geometric, this is just r, and do we need to take the limit of anything? No. For a geometric series, this ratio is in fact always the same. It doesn't change ever. So it's not like we have to take the limit or anything. But for a series that is not geometric, maybe we can still kind of pull the same trick, right? If we do one term divided by the previous term, we don't always get the same thing, right? We don't always get the same thing. But maybe the thing we get, the ratio between one term and its previous term, maybe that approaches some number. Let's call it L. If it approaches some number, like 1/2, then what does that mean? It means that if you take the 500th term and divide it by the 499th term, what do you approximately get? It means if the limit is 1/2 of this quantity, then that means that the ratio between the 500th and the 499th term is approximately 1/2, right? Likewise, it gets only better as you go out, right? And then, so that what that means is, yeah, after 500 terms or something, this is basically a geometric series, even though it's not at all a geometric series. Out at infinity, maybe it is acting like one, right? That's what this says on like a large scale. And so we're kind of hacking the geometric series rule up here to kind of make it usable for any function. Right? Maybe we can look at the ratio between terms for any crazy functions. And then these rules down here should sound absolutely familiar, right? Then, if it really acts like geometric, then we expect that series that has a limit of ratio between terms of 1/2, even though it's not geometric, to still kind of act out at infinity like a convergent geometric series. So that's exactly right. Likewise, diverges if our big L is greater than 1. Inconclusive if L is 1. Okay. That's the big trick. And now we're just gonna do an example, right? 2, 3 examples. Right, that was the big trick. So let's see if we can do it. I've already got the power series representation for some function. Who knows what it is? Doesn't matter though to us, right? We'd like to know where it converges. Okay, so here we go. This is how we're gonna hold your hand very carefully on this first one. This is how the ratio test works. First of all, before we do anything else, let's all recognize that this is not geometric. Do you agree? It is almost geometric, except for what? We like the x minus 5 to the n. We actually like the 3 to the n too. But the n means that this isn't geometric, right? You see it? This guy right here. It's almost geometric. If this was 1 over 3 to the n times x minus 5 to the n, it would be geometric. Okay, so here we go. We're going to compute our L value by taking the limit as n goes to infinity of the ratio of the next term to the current term, right? So plug in n plus 1 everywhere and divide by this. This is what we have here, right? Don't look at the n part down here yet. So do you see what I'm doing? I'm plugging everywhere there's an n in our formula, I'm replacing it with an n plus 1. And then I'm doing that divided by an, which is just a formula that's inside the sum, right? Is that okay? So this is our formula with n plus 1 plugged in. This is our formula with just plain old n still in. There's still a big absolute value on the outside. There's still an n limit as n goes to infinity. And then now the rest is algebra. All right? What did I do on the next step? Can you tell after the equal sign? What did I do? Well, the first guy, I just popped x minus 5 to the n plus 1 into the numerator for convenience. On the second guy, what did I do? I flipped it upside down, right? Because I didn't want to deal with this nasty. I mean, right now, the fact that I even wrote it this way is a little bit convenient, right? But I mean, what we have is this gigantic nasty fraction, and I'd like not look at a big nasty fraction. Now I only have one fraction, really. Is that okay? I'm going to just keep simplifying. This is going to be a very common feel for us. What did I do here? What did I do? 3 to the n plus 1 is 3 to the n times 3, right? So I can cancel out all of these, leaving just a 3 behind. Yes? I mean, imagine, put a number if you're not convinced. This is 3 to the 5th, say, and this is 3 to the 6th. Okay, so we cancel them out. We have 1 left, 1 3 remaining. Well, actually, we can pull the same trick here and here, can't we? We have something to the n plus 1, and so this cancels, both of those fully cancel out, leaving just behind an x minus 5, right? Can't really do anything with the n plus 1 and the n. I'm just cleaning things up. Make sure you're okay with this next step down here. You okay with that? Can you get it to there? That's it.
Pull the x minus 5 up because then there's nothing to do with that.
Exactly, yeah. Right? X is not the thing we're taking the limit of here. Now, let's make sure that we're clear on this. Because again, this trick we're going to do every time. In fact, it happens so often that you can just start by doing that if you like. I mean, you know this is, you can get a little quicker with this work as you get better at this. Like for instance, I would probably skip this first step almost always. Because it always happens, you know, I'm doing this so often in my life that I might just start by writing down that second step. You know, so you can quicken the work up. I want to just be really clear this first time around. So here we go, we're going to keep going here. And now the limit as n goes to infinity of this nice expression is something like a pre-calculus student can do, right? 1/3. And we still have this absolute value x minus 5 hanging around. Yeah, sorry. Because for any given x value, you fix x for a second, take the limit as n goes to infinity. You want to do this again? Pick another x value. All right, you picked it? Good. You got one in your mind? Okay. Now let n go to infinity. What happens? Okay. The point is, the value of x you pick doesn't come in to the equation for when I take the limit as n goes to infinity, right? It's not involved, right? For any given x value, I mean, you can leave it inside if you like, right? But you want to treat, when you're taking this limit as n goes to infinity, you want to treat x as if it's like 42 or something, right? It's just a number. Well, thankfully we don't have to think about that right now, do we? But, I mean, we could, right? Yeah. For any given x value, this is just some numeric series, and we would like to know in general, when does it converge, right? All right, now, again, if we want this thing to be a convergent series, let's pretend that it is convergent for a second, right? That would mean we require that big L, this thing here, 1/3 times the absolute value of x minus 5, be less than 1, right? And if that's the case, then what are we really requiring? We're requiring that the absolute value of x minus 5 is less than 3, and we have just found the radius of convergence, right? Does that make sense? So again, to be clear, what this means is that this converges for sure between 2 and 8, right? Outside of that range, for sure, it diverges, for sure. At 2 and at 8, we don't know yet. Save that for later, okay? Do you understand what we're saying here, though? But today, the goal is just to name what the radius of convergence is, and we just did it. R equals 3. Done. Yeah.
I'm pretty confused how you conclude that R equals 3. What is R?
So we said R is a number for which, when we do this, x minus a is less than that number R, right? We just determined that that must be 3 by the form of the algebra, right? Yeah, probably.
5 up there, that's A.
That's A. Yeah, 5 is A.
But the one up there where it says limit as n goes to 3A and sub n plus 1, is that the same A as 5?
No, I'm sorry. Yeah, maybe we should use like some u sub n plus 1 and u sub n or something. I apologize. Yeah. I know we've got all these A's floating around. I didn't even think about that.
Once you solve like for model and you absolute value of x minus 5 is smaller than 3, why do you conclude that R is 3?
Yeah, because R, remember, here, let's go back just for a second to the definition of what R is here, right? Where is it? Right? So R is a number such that the series diverges for this, converges for this, right? We just determined that R series converges when absolute value of x minus a is less than 3. So R must be 3. Done, right? So we're kind of coming in a little backwards on that, right? But that's the idea. Right? Once we make this determination, we're saying, hey, R series converges when this is true.
So is there any significance
That must mean
to like
R is 3.
if you solve that for x, would there be any significance to like
Yeah, so again, if you solve this for x, you get the interval 2 to 8,
yeah.
right? And so let me say it again, right? What we're saying is that for sure, this series converges if x is a number between 2 and 8. For sure, it diverges for numbers outside of that range. But the reason we're still being somewhat nebulous and not saying this yet is because we're not sure about whether to say equals to on the endpoints. We don't know yet, because it's inconclusive at those endpoints, isn't it? When R, right, when the L value is 1. Okay. All right, so let's see if we can do at least one more here before we head out today. We're going to try and pull the same. I don't mean this to be any different in feel. Okay. So we're going to try and find that L value first. The limit as n goes to infinity of the next term. We'll write it out again. N plus 1 factorial. N plus 1 to the 4th. X minus 3 to the n plus 1. All right, there's the n plus first term. Divided by, or do you want to flip it right now? We can flip it right now. Divided by, oops, sorry, that's n to the 5th. No, I did it right. It's n to the 4th still. Yeah, what do we need here? We need an n plus, no, just an n to the 4th on top. And on the bottom, we need an n factorial and an x minus 3 to the n. All right, and then this is the fun part. We get to cancel things out, whatever we can see that cancels out, right? Leaving behind x minus 3. What about the n? What about the factorial stuff? Can you talk to me about that? Yeah, what is n plus 1 factorial over n factorial? N plus 1, isn't it? All right, so we're catching all this stuff. Here we go. N plus 1 on top is still what we have. X minus 3, n to the 4th, all over n plus 1 to the 4th. All right, I think that's what we have once we clean up inside the absolute values. We can pull the x minus 3 out. It's still in an absolute value. So we can pull it out. Limit as n goes to infinity of all this stuff. Okay, and actually I'd rather not multiply this out. And I think you can be convinced that we don't need to, right? What's the absolute value? What does that limit evaluate to? To the 4th? Oh, yeah, we can cancel one out. You're right, sorry. There you go, that's fine. Regardless, what's the answer? We have 5th degree over 4th degree, or now, okay, now thanks to Emma. We have a 4th degree over 3rd degree.
This part is interruption for 2 announcements.
Doesn't matter what x
This
is.
is the afternoon park reminder.
Right.
Ms. Petulante's 6th period Algebra 2 class. You are to report to lab 253 at 11:10. Please go get your lunch as soon as possible and be in lab 253 by 11:10. We will start without you. Also, if you do need an English makeup, those makeups will not occur this afternoon. Repeat, they will not occur this afternoon. They will be occurring on Monday the 23rd, and you will receive a pass with further information. Once again, English makeups will not be occurring this afternoon. They will occur on Monday, and you will receive a pass with more information. Also a reminder to any seniors who are graduating seniors who are interested in being a graduation speaker, we will be having our interest meeting in the main office at lunch. Please be there by 11.
It's race convergence. Zero awareness there.
So L is infinity, right? Regardless of what X is. So what does the rule say? There's always divergence, right? There's always divergence, except for one place. The center, right? Which is trivial enough, right? I'm passing out this homework. Hey guys, the instructions on this are just a little bit off. You just need to find the radius of convergence for all these. Find R for all these. Ignore the instructions around here. Okay?